Okay, welcome back everybody. Physics again today. So we're going to continue our discussion of unreal estate. And kind of where we left off yesterday was we were talking about the movement of the Earth. There's an axis, the movement of the Earth. And we were talking about geostationary orbit, which means it's over the same part of the Earth all the time. And we got to the point that we said, you know, if we go from here to here, we would have to go 7,910 meters per second or something like that to maintain orbit, right? And we got that data. I'll show you how to figure out that velocity and stuff according to force centripetal and force of gravity later, but we got that data off the internet, we believe it. And we figured out that how fast do we actually go at the surface of the Earth, how fast do we go? Cool. Okay, so velocity tangential at the Earth's surface is 462.96 and then some meters every second, right? So there's a big difference between 7,910 meters per second and that, so there's no way we could have geostationary orbit in low Earth orbit. Okay, so we started talking about, well, somewhere out here, then, is going to be where this hotel is going to be, because it's out of space, not inner space, like, you know, down in here somewhere. So our only other option, if this is going to work, is going to be out in space. And we talked about some commonalities between here and here. So my question is, what did we talk about as far as something that these two places had in common? Okay, so angle measurement. And to bring the angle, so angular displacement is the same from here to here as it is from here to here. Okay? And then we started talking about, is there a way that we can describe angular displacement? What did we say yesterday? Okay, so the question is going to be a simple answer, of course. The most obvious stuff is always the hardest to think of, especially when someone's asking that. So we're going to try to match angular displacement on the Earth's surface to angular displacement there, right? So if there's a displacement that occurs over what we call time, thank you very much. So what do you think would be a good description of how we are moving or displacing angles? Yes, that's correct. Thank you very much. Angular velocity. And so we described angular velocity as with our little omega, and we said that's the rate of change in rads per second. And we said that a rad is, did we describe actually what a rad is? What is a rad, or maybe we should call it a radian? What's a radian? Very good. An angle measurement. And how many radians are in one circumference or one circle? 2 pi. Okay. So we could say that a circle is made up of 2 pi radians, right? And if you want to figure out how many radians are, you know, per degree, you know that a circle also has 360 degrees in it, and we know it's 2 pi radians, so we can say that each radian is equal to 360 divided by 2 pi, or approximately 57.3 degrees. Right? Okay, so how long have you been thinking about this formula? Circumference is equal to 2 pi radians. When did you start thinking of this formula in that way? Please tell me. So here's like the time between, this is kind of the confusing part, because in 6th grade you learned that this formula. You learned this formula in 6th grade, right? Or maybe 3rd or 4th, or maybe 8th. How many of you have never learned this formula? Okay, so what does this formula mean to you? If you reset a couple days ago, what does this formula mean to you? 2 pi what? Radius, right? So that's what you're used to, that's what you know. So now we have to tie these two pieces together. So when I say circumference in this form, I'm not really meaning meters anymore. What am I meaning? 360 degrees, a full circle, a circumference of degrees. So this is talking about, if I sweep out 2 pi radians, that means I've come through a complete 360. I've come through a complete turn. I've come back to where I started. I did a whole circle in degrees. Okay? And I know you've used this formula if you're in pre-calculus, calculus. I know that you've used this before. So you can believe that. And the people that are just learning that now, well, you can start believing this because it's the truth. But it's a little bit different thought. It's not circumference in meters anymore. Now it's circumference in degrees or angle. To further kind of talk about this idea, if I sweep out a radian here, that's 1 rad of angle measurement. If I sweep out a radian here, that's 1 rad of angle measurement. See how this radian of measurement, or angular velocity, this is what we're going to find in common on Earth with what we have out where the space hotel is. Like if I go like this with my arm, which you can't see on the video, some of this, how this sweep is similar. So a radian is this much of a circle. 2 pi radians in 1 circle. Okay, so I got a question here for you. Because in order for us to have similar in order for us to tie exactly to the Earth in what we call a geosynchronous or a geostationary orbit, that's not for us, that's for the city, right? We need to make sure that for every amount that we move in this way, in angle measurement, so we could just say 57.3 degrees per second or whatever, if it was 1 rad, or just forget that I said that. We need to make sure that these two things are equal in the way that they're displacing an angle, right? And so yesterday, a radian, by definition, is an angle measure that's equal. Then there's in every circle there's 2 pi radians of angle, which is about 57.3 degrees. Okay. Okay. So the question is then, we need to find velocity tangential out here that is going to match in angle sweep velocity tangential here. Now, look at my arm. Are those two velocities going to be similar? Actual velocity, tangential velocity. Like if I'm right here, why do I go there when I'm on the merry-go-round? Because I'm old. Because I just barely turn around, which means the little things in my head, the fluid inside my inner ear doesn't make the hairs bend as much. Because, that's what makes you dizzy. When I'm out here, though, I really feel that. Okay, so what's the difference between sitting right here and right here as far as velocity? Harrison. Okay, so that was a great mind experiment. Thanks for writing the carousel of the merry-go-round. So we have come up with this there's a difference in velocity tangential, even though we have a similarity. And that similarity is what we need to tie the Earth to the space hotel, and that similarity is the angle measurement per time. Thank you very much. Okay. So, one thing that you may or may not have picked up here is, I got a question for you. If we look at this formula, 2 pi rads, 2 pi meters or radius, okay, let me ask you something. How does radius have to do with distance or displacement as far as your circular path? Anyone know? Let me ask you in another way. If you have a radius of 2 meters, could you tell me how far you're going to be displaced if you go around one complete circle? Okay, so yeah, so this is what you knew before, right? So circumference equals 2 pi, and that's in meters. Circumference in meters is 2 pi radius, which is in meters. So if I have a radius of 2, then my circumference in meters is 4 pi. That's my distance that I travel. If my radius is 2, and I go all the way around once, my total distance is 4 pi. Well, let's say that your radius is 3. Well, now your circumference in meters is 6 pi, right? You can get a number out of that because pi is a number. You can pretty much get a number out of it. Not as good as pi, of course, right? But, okay. So my question to you is, or no, I don't have a question yet. I got to tell you one more thing. If I sweep out, okay, let me ask you this. This is the tie right here. You told me that for every circle there is 2 pi rads, right? Swept out. For every circle, you said there's 2 pi radius. Okay. Could someone tell me how many arc length measurements in terms of a radius are in a circle? So the question that jumps out right away is 2 pi, because, that's what the formula say, and, some of us have already, got this in other places. Okay, so what you're saying here is an arc length, they say arc length because it's not a line, in distance is equal to 1 radius in meters. If I sweep out, how much angle? 1 radian. So if I sweep out 1 radian, in turn, my arc length in distance is equal to the radius. Okay? So, we're going to go on, because I need you guys to do something here. So I'm going to say right here, we know the radius of the Earth, and we're trying to find the radius that we need to put our space hotel at. Now, I got to tell you, you will not be able to figure out the radius until I teach you about the force of gravity and the force centripetal and the acceleration centripetal, and throw some or explain some formulas and relationships to you. You won't be able to find this today unless you know that stuff. But what I do want you to find today is a formula for tangential velocity in terms of angular velocity and radius. Because I know I'm going to have 2 different radii, here and here. So, and the one thing that I do know that has to be the same here and here is angular velocity. So this is our go-between. And we're going to need to come up with some formula for velocity tangential in these terms in order for us to start doing the computations that we need to do the space hotel. So you got 20 minutes here. I'm going to see if you guys can do this as groups, your lab groups. And we'll come back and discuss what you do here in a little bit. Okay, everybody. Well, you did a good job. And I guess kind of what we came up with here is, you know, circumference equals 2 pi rad, or radians. So 1 radian is equal to circumference divided by 2 pi. And we also see that circumference, and so that's, you know, angle measurements, rad. Circumference also equals 2 pi radius. Okay, so 1 radius is equal to circumference divided by 2 pi. So it's hard to do the transitive property, I guess, I think it's called, with this because, you know, one is a meter and the other thing is an angle measurement. So I'm not sure how you go about doing this mathematically, but conceptually you can say that 1 rad sweeps out 1 radius of distance. So if we have our circle here and we sweep out a full rad, then in arc length we sweep out 1 radius. So for at this point those two distances are equal. If we go a little further out, then these two distances are equal. Okay? So with that understanding, we know that angular velocity is going to be equal if we're going to have a geostationary orbit. This angle sweep has to match this angle sweep per time in order for us to, you know, maintain that common line that would be, you know, making up the two radii. So we know that the angular velocity is the same. And since angular velocity is a rad per second, and if we conceptually understand that when we sweep out 1 rad, we go an arc length equal to 1 radius, then we can say that if we take our rad per second and we multiply it by the actual radius in meters, then we can say that we know our meters per second. So if we have an angular velocity of 1 rad per second and our radius is only 1 meter, then our tangential velocity is equal to 1 meter per second. If we have 2 rads per second, and our radius is still 1 meter, then that means our velocity tangential is going to be 2 meters every second. Because I did 2 rads of arc length, and I know that each arc length sweeps out 1 radius, which in this case is 1 meter, my velocity tangential is 2 meters per second. So, in the end, the formula, velocity tangential is equal to angular velocity in rads. Now you can't do this in degrees because the rad is the go-between, the 1-to-1 ratio, times whatever radius you're at. So this is the final velocity that we came up with. I would like you guys to do a lab to show that this actually works. You get a buggy, some string, a tape, a marker to make marks on the string, and you get a timing piece if you need one, which you don't actually need one, to show that this works. Okay, have a great day. Thank you very much.